All right, we're on. Before we start with the topics of today, I wanted to bring up that we have the procedure handbooks, and I, uh, I hope to use the book for one of the quizzes. So I hope all of you are going to get the book. We have enough for everybody, and for that you can contact our TA Alejandro, who gave the seminar on Tuesday. All right. When we started to talk about welding processes, we decided to start with arc welding processes. Our first stop was arc welding processes in which the electrode was non-consumable. And we talked about gas tungsten arc welding, TIG. We talked about plasma arc welding, including a particular flavor that is much used in Canada to make wear-resistant overlays, which is PTAW. And then we said, all right, the next level of complexity from the point of view of the mechanics is when the electrode melts. And then we start to discuss the case of the case of MIG, the case of metal core arc welding. And then we said, okay, if we add the level of complexity a little bit more, how about if now, in addition to the electrode melting, instead of a gas shielding, we use fluxes to shield the molten metal. And we discussed, towards the end of last class, we discussed flux core arc welding, in which everything is pretty much like in MIG, except that now we have fluxes inside the core of the wire that melt and protect the molten metal. And in some cases, we have a little bit of gas, and we call it flux core G, right? Or some other times, we don't have gases, and the fluxes do all the job of protecting the metal and purifying it. That would be flux core S for self-shielded. And then at the very, very end, we start to discuss this very interesting process of submerged arc welding. In submerged arc welding, everything is very much like in MIG. We had said we can use a solid wire. It doesn't need to be a flux core wire, except that instead of having an inert gas shielding and protecting the molten metal, now we have the whole weld happening under a bed of powders, fluxes. Now I'll show you a few videos that is going to make this clear. And I made the clarification that in subarc welding, we are not welding underwater, right? Submerged is submerged under fluxes, not submerged underwater. And we saw what are the characteristics in subarc welding. How do we protect the subarc weld from how do we protect the melt from the oxygen and nitrogen in the atmosphere? We have the flux, and we mentioned very briefly something. I will just use words, but there is one word called basicity. I believe we're gonna get a little bit deeper into detail on this if we have time when we discuss fluxes. But depending on the chemical composition of the fluxes, the resulting weld might have more or less oxide inclusions. Also, there is another word that is called neutrality. And neutrality controls how much manganese and silicon are going to be in the molten metal. And this is relevant because manganese and silicon are very effective deoxidants. So if we are welding on a rusty plate, typically we want to have a molten metal that is relatively high in manganese and silicon, such we can scavenge all this oxide that forms, and and give us a weld of good quality. I have a question here that is if basicity is equivalent to alkalinity, and the answer is no. Although there are reasons, there is some amount of connection. Calling alkalinity is related to pH in aqueous solutions. In this case, we have no water nowhere. However, out of a tradition of steel making, people use refractories that they called basic or acidic during steel making, and that has particular reactions with the slag. When the fluxes now have a similar compositions that would relate to these steel making practices, they call them acidic or basic. For example, if they have more magnesium oxide, they tend to call it basic. If it is like more silicon oxide, they call it more acidic. I believe somewhere, somehow, probably there will be a reason why they call basic an oxide of magnesium and why they call acidic an oxide of silicon. But I have not found that reason. Nothing to do with pH. All right. The fluxes are extremely interesting because they give us the possibilities of playing games with the weld. For example, we can add alloying elements together with the fluxes. So when the fluxes melt, we are also melting alloying elements, and this way affecting the composition of the weld. That is, opens possibilities that are not open, for example, in the case of MIG. And because in the fluxes are outside the electrode, we can have a lot of whatever we want to have. We are not constrained to the size of the wire, as it is the case of flux core, in which all the fluxes are inside a tube, that is the wire, and there is relatively little room for putting things. The fluxes are powders, and there are two large types of these powders. One type is called fused. That is pretty much crushed glass. And this is the oldest type of flux. And as you know, when glass gets hot, it melts down, and this molten glass creates an insulation between the molten metal and the atmosphere. And this molten glass is essentially inert. It doesn't react with the melt. Now there is another type of flux in which the powders are made out of agglomerations of other components of other powders, including, for example, metallic alloying elements. And these are called agglomerated. Fused fluxes, because they are essentially crushed glass, they tend to have very low moisture. Agglomerated fluxes tend to have, we have to be careful to make sure that they don't absorb too much moisture. They could evaporate and create problems of hydrogen when the moisture decomposes into hydrogen and oxygen in the arc. This yeah, I was going to tell you something else about these agglomerated fluxes. Oh yes, I remember. So in the case of fused fluxes, because they're essentially inert, we can pick up the slag from welding and crush it again and reuse it. Of course, there is a limit because every time we use it, it's likely to pick up contaminants. But with fused fluxes, we can play some of those games. With agglomerated fluxes, when they melt and turn into slag, the solid slag, we can also try to crush it, and many people try. But the agglomerated fluxes tend to have more reactivity with the melt. They can have different basicity. They can have different neutrality and add or take away silicon or manganese. So when agglomerated fluxes, people try to either not recycle those or recycle them in very small parts inside a batch of new powders. How do we add filler material in the case of subarc welding is through unspooling a wire. right? It can be solid wire, can be metal core wire, and the wire tends to be a lot thicker than the case of MIG. There is no autogenous subarc welding, right? Similar to MIG, there is no autogenous MIG because the electrode melts. Polarity, this is very interesting in the case of subarc welding. Typically, we run it in electrode positive, very similar to MIG, and the reason is it gives us a stable arc when the plate is the cathode. Many modern machines also have AC, alternate current. And when we have alternate current, it gives us a possibility of tailoring the amount of melting wire and the amount of melting plate. And we will discuss that in detail when we discuss the physics of plasmas. They can have waveforms too. These machines are inverter-based machines and can have sophisticated electronics and programming. However, typically, and only very recently, we start to have waveforms other than the square waveform. So what is typical in subarc welding, when you see a waveform, in a modern machine is a square waveform. The reason is you don't see the metal transfer to design sophisticated waveforms the way we have designed sophisticated waveforms for MIG. These machines tend to run in a number of different combinations. One is CV, constant voltage. In that aspect, is very similar to MIG. We set a wire feed speed, we set a voltage, and then the current will be whatever current that is needed to maintain that voltage at that wire feed speed. That is common. Now, when we're trying to go to higher currents, we use something that in submerged arc welding people call constant current. Now, here's a word of caution. When we talk about constant current in TIG, that means current is constant, and as I change the arc length, I'm changing the voltage. That's for TIG. But when we talk about constant current in submerged arc welding, means the constant current is constant, but also the voltage is constant. And now this is interesting. Pretty much everything you have seen in your life, you get to choose the voltage or you get to choose the current. But very, very, very seldom, and outside these machines, I don't know anything else, you don't get to choose both voltage and current. Now, how is this possible? Well, in this case, if you set the voltage and you set the current, then it's the wire feed speed you don't get to set. And the wire feed speed will accommodate to whatever it needs to be that keeps the same voltage, which means same arc length, and the same current, which means same arc force, right? And the wire feed speed doesn't vary very much. And when you look at data acquisition signals, you see how the wire feed speed varies a little bit higher, a little bit lower, a little bit higher, a little bit lower. I have a question. Okay, a question is, if this is due to the ability to vary the resistance of the wire based on the wire feed speed. The answer is no. It is possible to set current and set a voltage, because by changing the wire feed speed, I'm changing essentially the load we have. If, for example, the wire starts to come too close to the electrode, typically in MIG, I would increase the current. But in this case, I cannot increase the current. In subarc weld, I cannot increase the current because it's constant. But what happens if the wire starts to get too close to the plate, I detect that the voltage is too low, and what I do is I slow down the wire feed speed. But this has nothing to do with resistances. This has everything to do with a balance of mass and energy, which we will see in detail later in the class. So this is an interesting thing. So let's keep in mind that while we run MIG in constant voltage and TIG in constant current, when we say subarc welding runs in constant current, is something very different than the constant current of TIG. All right, characteristics of submerged arc welding. In submerged arc welding, we make very big passes. So I mentioned that if PTA is like a scalpel and MIG is like a knife, submerged arc welding is like a chainsaw, right? Like we can, with a chainsaw, we can cut the very big things and very quickly, as long as we don't care about precision cuts. And so arc welding is more or less like that. We can make very big passes, but these passes will have a bigger heat affected zone and are gonna be wider beads too much deeper. So the only way of making even bigger passes would be using electrogas welding, which we discussed on Tuesday, or using a casing that is called electroslag welding, which I'll discuss later at the end of this set of slides. Submerged arc welding is typically mechanized, which means is put on something that will move the torch automatically. That doesn't mean having any computers or anything. You just put it on a little cart that moves. Typically, it works on the flat position. Of course, people have tried to do subarc welding even in the horizontal position, but you typically run it flat. And there are a couple of reasons why this makes sense. One reason is that the fluxes don't want, it's very difficult to stick a flux to a wall, right? Although there are tricks that you can do trying to hold the fluxes, and people have tried, but typically fluxes wouldn't stick. That's one problem. Problem number two, and reason number two why subarc welding runs in position 1 flat, is that subarc welding is meant to have big passes, big productivity. And in the horizontal, in the flat position, gravity helps you to keep the weld down. But if I wanted to do a subarc weld in the horizontal position, now gravity wants to make my weld sag and fall to the side, right? And if it is small, surface tension can be okay. It's the case of MIG or the case of flux core. But if the weld starts to be very big, as we mean it to be in subarc welding, it's gonna sag, it's gonna roll down. So subarc welding, flat. Very high deposition rates, and this relates to very high currents too. In MIG, a large big machine, a MIG machine reaches 400, 500 amps. In subarc welding, a standard subarc welding machine reaches 1,000 amps. Right? And the machines look and feel they're quite different. And we're preparing videos to show you, so you see those machines in operation. Applications. Okay, subarc welding is typically done in the shop. Although I have heard of people mounting a subarc welding machine in the back of a welding truck. You could, but subarc welding typically makes large welds, and you need this mechanization to make a little tracks. You seldom do this by hand. Because it's mechanized, the operator doesn't need to be a welder. And where do we use subarc welding? In pretty much everything that is large and thick. Shipbuilding uses this, making line pipe, civil construction. If you remember my story about the Battle of Kursk and the T-34 tank, one Panzer could kill 7 T-34s. The German Panzers were welded by hand, and the T-34s were welded using submerged arc welding. That was the first mainstream application of submerged arc welding. Let me see, I have a question here. The question is that when I mentioned constant current subarc welding means constant voltage and constant current, both constant, although we say only constant current. And it says there is no adjustment of the arc length as the weld is being deposited. Right, the arc length is, it's no manual adjustment. It's an automatic adjustment. In subarc welding, if the arc length is too short, you know it because the voltage would be low, and then what you do is slow down the wire feed speed. If the arc length is too long, you'd see a voltage that is too high, and then you increase the wire feed speed.
Okay, so does the operator manually do that?
No, it's automatic.
It's automatic. Okay,
It's
so
automatic.
The machine,
The machine in this case, it just reads the voltage and current, and the wire feed speed is controlled by a closed loop control system.
Okay.
So the subarc welding machine we have in the lab is like that, for example.
Oh, okay. Thank you.
Yeah, and that's common. That is not a high-tech innovation. That's common. That the constant current is common.
Thank you.
One of the reasons to do this is that when you're at high currents and you have variations like the weld pool is moving, when the weld pool is moving, the arc voltage varies quite a bit. And when the arc voltage varies quite a bit, then the current would try to react to that if we are running in constant voltage, and we can have big spikes of current. Now, when we are running at constant current, the constant is going to be the current is going to be very even. The voltage is going to be moving around an average because of the oscillations of the weld pool. And if there starts to be a drift, the wire feed speed changes. And that is a relatively much slower response time, and the machine doesn't go crazy when it's operating at high currents. So Wes asked if those two variables, I suspect the two variables are current and voltage, result in arc characteristics. And by characteristic, I suspect is intensity of the arc and arc force. And yes, when we have constant voltage and constant current, the arc, especially with constant current, the arc tends to be very steady, which is, for example, the case of TIG. Let me see if you have sound. If you don't have sound, please let me know. I'm going to show you a video from the Society of Manufacturing Engineers about submerged arc welding.
In submerged arc welding, a bare, continuous consumable electrode wire, shielded by a layer of granular flux particles, sustains the arc. When the arc is struck, the tip of the electrode is submerged in the flux, and the arc is not visible. Welding proceeds without the intense radiation that characterizes open arc processes, and with little fumes. The submerged arc welding process varies from semi-automatic to fully automatic. Equipment includes automatic wire feed devices and joint tracking systems to move either the welding head or the workpiece. Submerged arc welding is commonly used to join all types of steel, stainless steels, and nickel alloys.
Okay, so that was interesting. Here it stopped at what is welded with this. All types of steels, stainless steels, nickel alloys. It didn't say aluminum. Oh, the audio was slow. Okay. Okay, I'm gonna raise the audio for next. So, yeah, these videos are not the paradigm of safety. Sometimes you get to see them doing activities without safety goggles too. But let's get to what is most interesting to us. A question of something I have not discussed yet, but some of you might have thoughts. It mentions steels, nickel alloys. Why not aluminum? I can make aluminum. I can MIG weld aluminum, I can TIG weld aluminum. Why I cannot sub-arc weld aluminum? Thoughts? Okay. So two of you mentioned oxidizing, and you are onto something. Oxygen is a huge problem, and so is hydrogen. What happens is that aluminum is incredibly reacting. Molten aluminum is incredibly reacting. Some people call it the universal solvent. Like you dissolve everything in aluminum. And there are some things you might not want to dissolve. For example, the fluxes, you want them to protect your weld pool. You don't want to dissolve into the weld pool. And people have thoughts about how to do sub-arc welding of aluminum. And you would use, instead of the fluxes, instead of being oxides, would be fluorides. We have even tried some of that in the lab. Most of the time it doesn't work. And when it works in a lab, but doesn't work in the condition of an industrial production. It's quite interesting. So sub-arc welding of aluminum, for which there would be applications, is an amazing technology of tomorrow, and every day is a technology of tomorrow. I don't lose hopes. I would love to see sub-arc welding of aluminum, but it's no commercial producer is right now pursuing it. One question is if the type of shielding required for aluminum is best in gas form. Of course. Always, if you can do something using an inert gas, you will always be better off from the point of view of purity. There is something else that is especially interesting about sub-arc welding. So let's see if I have something. Okay, I'll show you this other video in a second. In submerged arc welding, so we can make big passes. But when we make smaller passes, we use MIG. We seldom get to see, very seldom, people running submerged arc welding at, say, right? Because we lose. But why don't we use MIG then at 1000 amps? Anybody has a thought? Why not to use MIG or TIG at really high currents? All right, Eddie says shielding, right? And it's true. When you use very high currents, then you start needing to move fast. Yeah, and you have a very large weld pool. And we discussed already that a large weld pool has a lot of energy, therefore it takes longer times to cool down. By the time the long weld pool is cooling down, the torch has made a lot of distance, and this tail of the weld now is not shielded by the torch anymore. If we wanted to do very high passes with a gas shielded welding process like MIG or TIG, what they have is what they call trailing shields. And in Germany, they're even commercial. People typically make them themselves when they need. So you have the torch, and you have something kind of a little box that follows the torch and is having inert gas protecting that weld. So let me give you an example of something for which sub-arc welding of aluminum would be awesome, and in which we are doing MIG at very high currents. So when you sell, Korea doesn't have many natural resources. So they buy liquid natural gas, right? And some of that comes out of Vancouver. And that is in ships that have these big spherical tanks. You might have seen photos of these ships that have these spherical tanks. And those are made of aluminum of about 1 inch in thickness. And because you want to make them as automated and as fast as you can, right? You like to do one big pass or a couple passes and get done with it. But MIG and TIG have a very hard time with that. Sub-arc would be awesome, but of course we cannot do sub-arc. In the end, they use MIG in conditions similar to sub-arc welding, and lots of shielding. It's very interesting, but those are very anomalous processes. Now, one of the cool things of this class you're taking is every trick you want to know is in the Lincoln Procedure Handbook. That's the Bible. But because we have an understanding that is beyond the tricks, you can start thinking about things, about the relationship of current, the weld cross-section, cooling rate, time to cool, shielding, and if everything goes right, you'll never be afraid when you have a new thing to weld that people say, this is impossible. You'd say, I'm not too sure, let me think. And you'll think, and typically there is a possibility. This video is from the welding machine in our lab, and you should hear the sound of an inverter-based welding sub-arc welder. Here. Okay. What you saw there is not a problem. It's part of an experiment in which we did. And I'll show you the results of that experiment in the next couple of slides. So you got to see the flux powders. You got to see the torch moving. So I'll show you something that few people in the world know. But you will know because it's something we have done ourselves. And it is, how does what metal transfer in sub-arc welding look like? As you saw in the two previous videos, when you're at sub-arc welding, you just see powders. You see nothing more than powders, right? An occasional flash here and there, but very small. Now, if you want to do some sophisticated control of the weld pool, you might want to see what the metal transfer is. Things like, what is the arc length in sub-arc welding? Those things are not very well understood. So somebody in Germany, more than 50 years ago, did some experiments trying to observe metal transfer in sub-arc welding. And that work was forgotten for decades. And then, not too long ago, in our lab, together in collaboration with another friend from Germany, we tried to understand those old experiments and do them again, but in a better way. I believe the way we did it is better experimentally, and also now we have technologies so much more advanced than then, for example, in our high-speed cameras. So I'll let you think, based on what you know, what sub-arc welding looks like, right? And I'm gonna show you a video of sub-arc welding. I believe this one is at 500 amps, which is on the low end of sub-arc welding. So 500 amps. And what do you see here? This part, if you see my cursor, this is the wire melting down. This is the molten metal that is making a droplet. See how chaotic this is, right? It's not beautiful like MIG. Did you see the droplet fall out? This arch you see here is because we made a little bit of a tunnel to look under the fluxes. And of course, we have to validate this. And of course, I can show you the paper, and it's beautiful. See the droplet. This is at 500 amps. And it's somewhat like globular, but it's so so chaotic, right? And for sure, it's not the actual type of transfer. See how the fluxes are coming in. And this cavity that you see behind, those are molten fluxes. And you might wonder what the arc is. This is not argon, this is not CO2, right? This is vaporized fluxes. And people don't really know very much more about this. So we wrote a paper that we published last year with doing a survey of the last 100 years of subarc welding and all the research that has been done in it. What gas is in here? Right? What gas? It's not very well known. Not very well known. Here you have the droplets coming out as the wire melts. So, and this is at 10,000 frames per second, and we're rendering it at 30 frames per second. So this is a microscope of 300 times slower. Quite interesting. So, don't I have for 1,000? I wanted. Let me see if I find 1,000. Well, I don't seem to have metal transfer at 1,000. Okay, let's see. No, I don't have it. Question then, subarc is often run on a MIG machine like flux core, true or false? Of course, false, because the machines for subarc welding are a lot bigger. And I didn't have the video to show you, but when you're 1,000 amps, the metal transfer mode looks quite a bit different. It's very interesting. And here I have a photo. When we did this survey, this historical survey of science behind subarc welding, you can do subarc welding by hand, as long as you can rest the torch against a groove, for example. And all you do, the operator does, is keep the right angle and the right travel speed. But they don't see what they are doing. And we have this photo of a weld operator in the Soviet Union. I see no safety goggles. And he seems to be, I don't know, watering the plants or something, right? But that's subarc welding done by hand. Not very common, but not impossible. I want to move on to one more arc welding process that is that uses fluxes. This welding process is a business suit. Yeah, a leather business suit had our friend here in the Soviet Union. So the electroslag welding is typically classified with arc welding processes. So I will discuss this in arc welding processes. But let me tell you something funny about electroslag welding. There's no arc. There's no arc. How does it work? In this case, we have a wire. This electroslag welding is very, very similar to electro gas welding with similar applications. So here we have one thick plate. We might be making a ship or a really heavy storage tank. Here we have the other plate. So this would be an open square butt joint. No groove, no nothing. So this is moving vertically, and if I don't weld it, I could see from one side to the other, from inside the ship to outside the ship. Now, what people do is put these backing pieces. Typically, these are water-cooled shoes, left and right. So they're blocking this line of view through the plate. And these shoes, together with the joint prep, make a little bit kind of a square joint prep, right? And then I start melting the electrode and I move up the shoes. So I have solidified weld metal. The shoes that are water cooled move up, typically made of copper, so nothing stick to it. It moves up and the wire melts. It melts a little bit of the workpiece that in this case is not clearly done, but of course you melt a little bit of the base plate and you move up. Electroslag. Yeah, electroslag welding. Yeah. In the terminology, our set of slides on terminology, we have all the acronyms and names of the welding processes. what is different in electroslag and electrogas welding? What is different is that in this case, there's a lot of fluxes and you melt the fluxes. So you don't have a gas. In electrogas welding, yeah, you have CO2 typically. In this case, you have the molten fluxes. And there is no arc here. There is no arc. Typically, the fluxes are high in fluorine, are high in fluorides, for example, calcium fluoride. And the one characteristic of fluoride type of fluxes is that when they are molten, they are electrically conductive. So instead of having an arc, what you have is a flow of current that goes through the molten slag, and the droplet falls across. When we have a lecture on metal transfer that is going to happen a couple weeks from now, I have a video of this for you to see. That is a video made with, I have two, one made with X-rays and the other made against a glass plate. Very, 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 very interesting. And this process is not very well studied. It is to be expected, of course, that we're going to have pinch forces and electromagnetic jets in the molten slag. I have never seen a paper on that. If you want to study something exotic and for which all the pieces of the understanding are there, but nobody put them together, here you have one, much used in the heavy industry. Okay, how do we protect the melt in this case? Fluxes, while before it used to be gas for electrogas. The filler material is automated wire feed, can be solid or can be metal core. And this matters. Let me tell you something. When you're welding something with a consumable that is more or less the same, which we call homogeneous weld, still is not exactly the same, because the plate was rolled and maybe even heat treated, but for sure it was rolled and has very different properties than the microstructure of the weld that was molten metal that went solid and nobody ever rolled it. How do you make this cast structure of a weld to have as good properties as rolled material? Not trivial. So people add a little bit more things. For example, welding wire often has some amount, a little bit of titanium, which we're going to discuss what for when we discuss metallurgy, right? So sometimes if you need to have a lot more of those alloying elements, you can have a metal core wire. Polarity, typically electrode positive. Characteristics, this is what will give you the biggest passes. This you're going to see in welding of thick plate. You're going to see it in welding of thick members in civil construction. As you go up, you can see it in shipbuilding. Of course, this is mechanized. The way this swimming pool of molten metal moves up is through a system that is mechanized, very high deposition rate. You don't need a welder to do this. It's just an operator. You don't need eye protection because everything is deep under the fluxes, and you don't even have an arc, right? This has, similar to electrogas welding, a very big heat affected zone. If going back to our general concept, if the cross section of your weld is huge, means you melted lots of material, which means it's going to take a long time to dissipate the heat, which means the material is going to be hot for a long time, experiencing coarsening and having penetration of these thermal effects. This is good for shop welding. It's good for welding outside. Typically is square grooves in welds for butts. You can do this in a T-joint too. And, oh, okay. So that is electroslag welding. Now that we talked about all these, in practice, these processes I mentioned to you, electroslag is not very common. Even subarc welding, many welders have never seen a subarc welding machine. But I want to show you what everybody knows, and you have seen. This is shielded metal arc welding, what people call stick welding, what people used to call electric welding, as opposed to acetylene welding, right? This is what you typically see. This is what we see in our province all the time, a lot more time than we should. Stick welding, right? Is when you are going to learn welding, is typically the first thing they teach you. It's cheap, it's simple, requires a reasonable amount of operator skill, but not a crazy amount of operator skill like TIG. And but I left it last. And the reason I left it last is because in this case we have all the complexities plus a new one. Now we are melting the electrode, we're protecting the electrode with a flux, and now the process doesn't even run in steady state. We're not unspooling a wire like in MIG, we're not unspooling a wire like in subarc welding or like in flux core. We have a stick and we start burning the stick until we finish. And then we change and we start a new one. Let's see. Oh, here we have this photo. I showed this photo to you on the first day of classes. And here we get to see the weld pool. At the time, this looked like just yet another weld, but now things are gonna make a lot more sense to you. Here we have the molten metal of the weld. Here behind we have the solidified weld. Here on top and bottom, right? We see the base plate. What we see here is the electrode, and actually what we see on the surface, that's the flux cover of the electrode. That's when they call it shielded metal arc welding. The shielded is all these shielded fluxes are around the electrode. It's outside. Remember, in flux core, it was a tube with the fluxes inside. Now the fluxes are outside. Here we have the arc. And how do we protect the melt in this case? This is somewhat similar to a self-shielded flux core, right? It's the fluxes in the electrode that give the protection. But now we can have much more flux than we had in flux core arc welding, right? So now we can, before we could have a tube with a little bit inside. Now we can put outside as much flux as we want. And we can do so many things. For example, we can have materials that will give gas, right? So to some extent, we have somewhat of a shielding gas. One of those, for example, is the cellulosic electrodes. Cellulose, if you remember, is essentially paper. That's what makes paper. And originally, they invented the cellulosic electrodes by wrapping the electrodes on newspapers. And what happens when the newspaper, or in this case, the cellulosic fluxes, burn out? They generate CO2. It's a shielding gas, much like in MIG we use CO2, right? But because cellulose is an organic material, it also has hydrogen, which hydrogen makes the arc to be a lot narrower and more concentrated. So these cellulosic electrodes have this shielding gas generated by the CO2. They have a very powerful center arc because of the hydrogen. And these electrodes can cause us headaches because this hydrogen, when we weld steel, can result in cracking. And if you remember when we talked about the name of the passes, for example, in pipeline, we said we have a root pass, a hot pass, filler passes, cap passes. The root pass is typically done with this cellulosic electrode that can have hydrogen. Then we follow up the hot pass with an electrode that looks more or less like this, but it's low hydrogen and help us like heat the hydrogen away, right? Very interesting. So much like everything that has fluxes, I mentioned this for subarc welding, but it's also true for flux core, and it's also true for stick welding. the fluxes, we can have basic or acidic fluxes, right? And this basicity or this acidity controls oxygen. Typically, the basic fluxes mean low oxygen. Acidic fluxes mean higher oxygen, but other advantages. For example, easier removal of the slag. Filler material in this case is rods, is not a wire anymore. Polarity. Now we run these electrodes in constant current, right? The same way we were running TIG. And for this reason, historically, many of the machines that could do stick welding could do TIG, right? They were good for both. And I have a question or a comment here. The comment is that cellulosic, and this is a practical comment, cellulosic electrodes need certain amount of moisture. Otherwise, the coating can crack off and give an erratic arc. And this is an interesting and important comment because well, you can have these electrodes wet. And originally, something people observed too way back in time when they were starting with electric welding is that rusty electrodes behave better than clean electrodes. Now, while in these cellulosic electrodes, having moisture is helpful and it's not much of a problem because we already have hydrogen anyway. There are other types of electrodes that are low hydrogen and for which you don't want any moisture and you have to keep in an oven so they dry out and they have the minimum possible amount of moisture and hydrogen. Okay. Okay, pointer feature on Zoom. Okay, so let's see. Pointer feature. Ooh. Okay, let's see. Mouse. All right, okay. Thank you for the pointer. Now I have a laser pointer on the slides. Thank you. Okay, so let's talk about, we were talking about polarity. Constant current. Polarity can be electrode positive or electrode negative, depends on the flux system. And that it comes specified when you buy the electrodes, what they recommend. Typically, people do not use waveforms when for a stick electrode. These are standard machines. Some machines, especially the old ones, could run on AC at 60 hertz transformer-based machines, in which you get from high voltage, low current from your coming from your electrical supply. You turn it into low voltage, high current for welding. So what is the characteristics of stick welding? Is extremely versatile. As long as you can bring your cable and your stick, you're welding anywhere you are, right? It's very cheap. The equipment is very cheap. You can go buy it in Home Depot. For anybody could have a welder if they want. And because you can have different types of electrodes, you can have different types of applications too. I put here only manual, although I have seen that sometimes there are ways in which you can play tricks and leave the electrode in a special holder that will burn itself. But for the vast majority, this runs manually. The skills are higher than in MIG welding. MIG welding is more sophisticated machine and thinks for you many things, but is much lower than TIG welding. The deposition rate of stick welding is not very high. And the precision of stick welding is not very high either. You cannot make very fine details like you would in TIG. So when you see sports things, Race cars, airplanes, those are welded with TIG, but not with stick. Depending on the electrodes you use, you can end up with high hydrogen. And even low hydrogen electrodes still have typically more hydrogen than TIG. The equipment is very cheap, I mentioned. Applications, well, applications outdoors is where this process shines, because if the wind comes, as long as it's not a hurricane, the shielding stays there. We don't have anything that is going to be blown away, like our very carefully tailored inert argon shielding, right? Everything that is like one-off, when you need to make one of something, grab the electrode and you go for it. And it's very, very effective. Field welding, repairs of pipelines, what people call spools, that is this like, kind of when you go to a chemical plant here in Alberta and probably around the world, they're made like Legos. And each of those modules, this kind of chunk of Lego that is big like a room, right, have a part of this chemical plant. And all these piping and connections there, those are called the spools, right? And the way you weld the spools here in this province is, for the most part, with stick welding and a little bit of flux core. I want to tell you something about stick welding. It's the reason I am here in Canada. Stick welding is not very productive. And every time you grab the electrode, you're already losing to pretty much everybody else around the world, because your productivity is more or less the same, but our standard of life is much higher. I came here to see if we could move our welding and manufacturing in the province one notch, like anything newer than the 75-year-old stick welding processes. If we can do anything like better than welding like 75 years ago, we're good. An obvious target is flux core, but there are many other things. And we're making some progress. But if we have a mantra, is how can we go to more productive welding processes in the province? Let me show you the SME video about stick welding.
Shielded metal arc welding uses a covered electrode consisting of a core wire surrounded by a concentric covering, which is a mixture of silicate binders and powders. These binders and powders serve as a source of arc stabilizers, fluxing agents, lubricants, gases to displace air, and metal and slag to protect, support, and insulate the hot weld metal during welding. The bare section of the electrode is clamped in a holder, which is connected by a welding lead or cable to a terminal of a constant current power source. The workpiece is connected to the other power source terminal. Touching the tip of the electrode against the workpiece and withdrawing it slightly initiates or strikes the arc. The heat of the arc melts the base metal in the immediate area, as well as the electrode core wire and covering. The molten base metal, core wire, and metal powders in the covering coalesce or fuse to form the weld. The equipment required for shielded metal arc welding includes either an alternating current, or AC, or direct current, or DC power source, welding leads, an electrode holder, welding helmet and gloves, and protective clothing. The process is effective for welding ferrous metals such as cast iron, carbon, low alloy, stainless, and tool steels, and non-ferrous metals including copper, nickel, aluminum, and their alloys.
All right. Does anybody want to call it on the aluminum welding with the stick welding? Yeah, all right, there you go. Yes, this is exactly the opposite of what I was mentioning about subarc welding. And yes, it is true. There is there are aluminum welds, electrodes. And if you look in the procedure handbook for stick weld, the section on stick welding, it talks about them. But let me tell you, they are not pretty. And yes, they involve all these fluorides I mentioned to you, and they require extreme care to give you not an awesome weld. But let's say you're in the army in the middle of far away from home, and you need to fix an aluminum component. Yeah, you'll be very glad that you have these electrodes. But few, if any, would recommend them for doing production welding. I know the person who designed those for one of the large companies and told me, I did those stick electrodes. I'm not getting into subarc welding because it's been a nightmare. Yeah, so very interesting. All right, let me show you a video from our awesome lab. This is to show you how engineers weld. Oops, nope. Well, there you go. Those who know how to weld are probably laughing. People say that's why you call it stick welding. the electrode gets stuck to the plate. You have to know very much what you're doing. It's not uncommon that your electrode gets stuck and you remove it. And in this case, yes, eventually, in this case, it was welding too. I want to show you two videos from our lab. Actually, these videos were the welder in one of these is Eddie, who's taking the class and commenting here. So this is stick welding using 6010 electrode that is cellulosic. And we're going to get more in detail about this type of electrodes later on. But I mentioned it has this powerful arc. And because it has a powerful arc, this type of electrodes create what the welders call a keyhole. And I gave you the heads up in our terminology class on terminology that a keyhole from a 6010 electrode, a cellulosic electrode, has nothing to do with a keyhole from laser welding or electron beam welding. So we're welding a pipe here, and this is the video of what it looks from the outside, and the next one will be the video of what it looks from the inside. So here we're going at 10,000 frames per second, so 300 times lower than real life. The electrode was held in the hand and it was weaving, but you don't see any of that, right? Because it's so much slow. What do we see here? This is a V groove. This is a V groove in the pipe. This is the molten metal. This is a weld. This is the edge of the electrode. This is the edge of the fluxes that are melting. You don't see the metal part of the electrode, except when it starts to melt. You see this part here? This is the molten metal coming out and feeding the weld pool. Right? And you get to see how the arc moves erratically, very quick. This is 300 times slower than reality. The arc is moving from the left and to the right. Let me show you what it looks now if you look at the pipe from the inside. Now, what do you see here? We're looking into the pipe. Here we have the edge of the electrode. Remember, this edge is the same edge we see here. This is the molten metal that is coming out. See, this is the molten metal that is coming out here. But now we are seeing it from a different angle. This shiny part, this is the weld pool that is molten. And here you see, and here you see the joint in the pipe. And the interesting thing here is we're inside the pipe, the electrode is outside the pipe, and we're looking through the pipe through the keyhole, right? That has very little of evaporation. Evaporation is what causes the keyhole in lasers and electron beams. In this case, it's just the force of the arc that is keeping this open. Isn't this amazing? And let me tell you, if I show this to you for any less than 5 minutes, then you're seeing less than 1 second of welding. That's pretty incredible how slow this is. All right. It looks as if it was held fixed, but no, this was held by hand. All right, true or false? Yeah, super false. I tell you, if stick welding was high productivity, I would still be riding my bicycle in the mountains of Colorado. But thank God, stick welding is not possible, and they decided to have a welding center of excellence in Edmonton. And because of that reason, you also have this class. I think we all won. Now that we have all benefited from the poor productivity of stick welding, we have to move on and make something productive, because otherwise we're not going to be here for too long. Strip cladding. This is a variant of submerged arc welding and can be done as standard submerged arc welding or as electroslag welding. The difference is the type of fluxes they would use. And of course, in sub-arc welding, you have an arc, and in electroslag welding, you don't have an arc. What is the trick of strip cladding is that the consumable is not a wire anymore, but it's a strip, right? And so this is good for making claddings, to make overlays, because it's so wide that it's like painting with a roller instead of painting with a brush. And for all other practical purposes, this is much like sub-arc welding, and it's done in submerged arc welding machines that have a special head, and the head, instead of being a head feeding a wire, is a head that unspools these strips. So can make these very wide passes. It's mechanized much the same. This is a type of process you would use to create wear protect, especially corrosion protection in the petrochemical industry. And it competes in some cases with explosive welding and roll bonding in making something that is all coated with a material of particular properties, such as corrosion resistance. What you have here is a comparison of dilution. I think I haven't defined dilution in terminology class, but we will discuss dilution later on. Dilution is when I put my electrode, I melt some of the base plate. If I melt some of the base plate, I'm mixing base plate with electrode. Now, if I want something that is corrosion resistant, you want a particular composition, which among other things is likely to be very expensive. Do you want to dilute that with molten base metal? Typically the answer is no. So how much you dilute, and there is a formula to calculate, but the numbers are intuitive to you. In stick welding, 25 to 30% dilution means the final weld has, if you do an analysis, 30% of the final weld came from the base metal. You're diluting a lot. Then you can have these other processes, but when you do sub-arc welding strip or electroslag strip, you can have as low as 10% dilution. And that's pretty good, right? With laser welding, laser cladding, you have close to zero dilution. It's so low, we cannot even measure it. All right, this is about arc welding processes with fluxes. I want to show you a slide about an arc welding process that is different to everything else we have seen. So I put it in a separate stock of slides.